In this lecture, we're going to be discussing the geometric relations necessary for calculating path lengths for the Dubins paths. We're going to discuss the basic building blocks of the Dubins path, and we're going to define the major components, centers of circles, arc lengths, and line definitions. So let's go ahead and get started. So here are the four cases that we've discussed that we're going to be delving into. Right? We'll start off with a circular arc, middle is going to be a straight line, and end with a circular arc. Okay, so to calculate which one is the shortest, we're going to have to calculate a few different things. First, and I'll just zoom in here, we're going to have to calculate the center point. So things to calculate. Oops, that's my highlighter. Okay. We need the left and right center points for both our start and end circle, or our start and end configurations. So depicted here, we have it as CLS, so our left circle to start off with, our right circle to start off with. We then have our ending, or our left end and our right end. Left end and our right end. And so again, this is left end. This would be our right start. So these are the center points of the possible circles that we're going to be doing arcs about. Next, we're going to have to define when we start, right? Or when we start executing the line. So we're going to call this, we'll call it Z1, and this one will be Z2. We need the Z1 and Z2. These are our transition points. So when do we start transitioning between executing a circle and a straight line, and then from a straight line back to a circle? Okay, so those are going to be our 2 points. Another thing that's related to this is the distance between these 2 points. So the distance along the straight line, and also similarly, right, we're going to have to calculate distance that we're staying on the circle. So distance along start and end circles. And just as a review, we're going to calculate the distance for each one of these four possibilities. Right? We're going to calculate the path length and then choose the path that's the shortest. So that's how we do our Dubins paths. Okay. Oh, another thing that I almost forgot is that we're going to have to calculate. So if we were to look here, we're going to have to calculate the orientation of this line. I'll call it the Chisabel for right now. So we need to calculate the orientation of the line. Now, a lot of these things are related, right? So once, for example, if we were able to get Z2 and Z1 right off the bat, then we could calculate almost everything else really quickly. So things are very related, but we're going to have to know all of these things to be able to calculate our path distance. And similarly, and I guess I left this one off. So to calculate the path distance, we're also going to need to know this, the orientation. We call that var theta, just the orientation of the line. And we'll have to know the orientation right here and we'll call this one actually var 2. The orientation of when we start the circle and that we start the straight line, and this line right here. Oops, now I'm just getting all messed up. So this one would be var2, and this guy right here will be our var1 when we start our circle and when we end it. And we're going to have to do that for both the first and second circle. So we have a number of things that we need to calculate. That'll help us calculate our arc lengths and our distances along the path. And we're going to do that for all 4 possibilities, and then we'll come in and we'll choose the shortest one. So let's go ahead and jump into some of that math. Okay, so as we look at this, we'll start off calculating just the centers of our circles and the arc distances along a circle. So we'll have, for each one of our circles, we'll have a right and left center point. So this is defined just as the position. This would be our right or left position, plus this r right here. This is our radius of our circle. So we're assuming we're executing the minimal radius possible. This is the course angle, and we'll talk about these guys here in just a second. This is just to, these are unit vectors from P to C, CR or CL. Right, so we have defined these unit vectors, and I only did the first 2 elements there. So we have a unit vector from our starting point to the center point. And we're going to have to do this for both PS and PE, so our starting position and ending position, as well as our starting orientation and our ending orientation. And we'll produce actually 4 center points. We'll have our CR start, our CR end, our CL start, and our CL end. All right, so we're going to do this for 4 different center points. Okay, so let's gain a little bit more intuition on this unit vector. So say we have, I'm going to draw our north and our east. So this is our north and our east. And say the orientation, this is going to be P, and this guy's right here is our orientation. So we have our starting point and our orientation. The reason why we have a plus pi halves and a negative pi halves is just to look at, we want to know what the orientation of the lines pointing to the right and the left are. So let's look at the right first. So if we come over here, we want to get, oops, I meant to keep that as green. We want to know what is the orientation of C right. Oh, yeah. So if we just look at this, there's a right angle between it. So to get from P to our center right, we need to follow a direction. If we look at, oops, if we look at chi, sorry, if we look at chi, we're going to rotate it by a positive angle of 90 degrees, right, or positive pi halves of plus pi halves from chi. So in other words, our chi r is equal to chi plus pi halves. Then the unit vector pointing from P to C. So the unit vector for the right, so this is pointing P to CR, would then just be equal to we'll have our cosine of chi r, sine chi r, and 0. So we're assuming we're acting in the plane. Okay. So that's to get to the right circle. And if we look over here at our equation, to get to the right, we do P plus R, which is the radius of our circle. So we know where our starting position is on the boundary of the circle. So our center is a radius R away. Then you see we have cosine of chi plus pi halves and sine of chi plus pi halves. Okay, so exactly what we had stated here. Now to get to the left, we're going to follow a very similar strategy. So we could do that. We have the angle here. Chi left is actually going to be equal to, we could write this as chi left. If we look at it, it's going to be a negative 90 degrees from our value of chi. So we could say that this is equal to chi minus pi halves. Because again, our z is pointing down, so a positive rotation was in the direction of the right, a negative rotation is in the direction of the left. So we have a negative, and we could add, we could add a 2 pi to get to how I've drawn it, or we could just note that, yeah, we don't need a 2 pi because it's the same. So we just take our chi and we subtract off pi halves. So we end up getting that to get to our center left, we have this negative sign. Oops, I better not put that. That looks like an equals. We have our negative sign to get to our chi left. Okay, so hopefully that makes sense how we get to our left and right centers. Now, we're going to calculate distance along an arc. So we have to calculate this based on whether we're going clockwise or counterclockwise. It's calculated slightly different, right? So if we're starting off on a circle, we're going to say that var theta 1, this is going to be our starting angle of the circle, right? So assume this is where our C, R, or L is, but that's the center of our circle. And the aircraft is starting right here. So this would be P, and we have our starting orientation. But so that we know that the aircraft is on the circle, and in this case we're moving to the right. So we're going to be going from this location, and we'll travel along the circle until we get to this location. Oops. I did it to the north axis until we get to this location. Okay, so our starting angle is at var theta 1, and our ending angle is at var theta 2. Right, so the question is, what is the arc length between these two? Well, it's just going to be var theta 2 minus var theta 1. Right, so we have, this is the total amount of angular change that we have on that circle. Now the distance that we travel along that is just going to be, since this is a radius r, we have our radius r times our var theta 2 minus var theta 1. Okay, so that's the basics of what we're going to do. Now we have to be careful, right? Angles are, we have to be careful with angles. We want this, we need this to be greater than or equal to 0. So we need something that's positive or non-negative for our arc length. And a valid angle, so if we did negative pi halves, well, that's valid, but if we add but that's not going to help us calculate the arc length from one to the next because we're going in a positive rotation. So we're going to add 2 pi to it. So that's going to be the same angle, but it gives us that positive amount of rotation because we are moving, right? We're moving clockwise, so we're going at a positive rotation. So we have to express things as a positive rotation. Okay, so that's what this is coming in. So the difference in our angles, var2 minus var1, or var theta 2 minus var theta 1 in a clockwise direction is going to be 2 pi plus var theta 2 minus var theta 1 if we assume that var theta 2 is in 0 to 2 pi. And we assume that var theta 1 is in 0 to 2 pi. Then doing this 2 pi plus that difference, and then we're going to take a modulus. So this bracket is just the modulus of 2 pi. So the goal here, this looks a little complicated, but the goal is really quite simple. Express the difference var theta 2 minus var theta 1 and make that exist in 0 to 2 pi. So that way we get this positive arc length and we can calculate the distance. Okay, so we do var theta 2 minus var theta 1, add 2 pi to it, take the modulus by 2 pi, and we get the distance, the arc distance that we're going to be traveling. Okay, so again, this is for clockwise rotation. All right, now let's look at counterclockwise. This one looks a little bit strange. We're going to actually write this. Again, we're using the modulus operator, 2 pi, and I would say this is plus var theta 1 minus var theta 2. Well, obviously, right? It's just I just rearranged terms. But let's take a look at this circle to see what we're doing. So we have our starting orientation, var theta 1, right? So this is where we start. And we're going to go to the end orientation. So we're going to start we're actually start on our circle. And since we're going counterclockwise, we're going to move around in a counterclockwise rotation until we get to var theta 2. Okay, so we're moving counterclockwise. Now, if we look at the arc length, because we just want a positive arc length to calculate our distance, we're not doing a negative distance. So if we look at the arc length, that's the same. So it's the same as if we started, right, at var theta 2 and did a positive rotation to var theta 1. So the arc length, that was backwards. Okay, arc length is the same as if we start at var theta 2 and end at var theta 1. Okay. So that's how we're going to just write it up. Right? If we'll notice the difference here. In the clockwise, we started at var theta 1, went to var theta 2, so we do var theta 2 minus var theta 1. And in this case, we start at var theta 2. We don't actually, but to calculate our arc distance, that's makes it simple. We start at var theta 2 and end at var theta 1. So we can think of it like that. Okay, so either way, we can now define our circles, and we can also, given the two angles that make up where we're going to start on the circle and where we're going to end on the circle, we can now calculate the distance between or of the path that follows that circle, right? Either clockwise or counterclockwise. Okay. Now let's chat just a little bit about the lines. And let me make sure I didn't miss anything here. Okay. If we take a look at the lines. We're going to have two different types of lines, right? And we actually have four, but really just these two different types, and you'll be able to see what I mean. So either we're going to be transitioning straight between them, right? So we have this straight between them, or we're going to be transitioning from one side of the circle to the other because we're changing orientations. So this one is, the circles have the same orientation. So this case, this is R and R. And we're going to calculate R, also the R and the L. Okay. Where we'd start off, start off on the right circle and end on the left. And I don't think I drew that very well. Okay. All right. And it's going to be a similar thing if we did left-left. So if we did left-left versus left-right, right? So we can see that we're going to be crossing, we're going to be changing the orientations. So I'm just going to erase the actual orientations, and we'll just start playing with, we have these two different types of circles. And the one thing we need to note is that the line that we draw is tangential to each one of the circles. That helps us have this continuous path. We can just straight transition from a straight line to rotation, or rotation directly to a straight line. This is very helpful, and this helps us define all of our geometry. So since it's tangential, here I'm going to do, in this case, here's our center, and it's going to be a right, center, right. And I should say this is our start and this is our end, right? The fact that it's tangential is we can draw, it's a 90-degree angle. Okay, and if I come over here, you can see I didn't draw that line perfectly well. It's a little bit hard to just draw it, but we have a 90-degree angle. Okay, so that's fantastic. So we have our line is tangential to our circle. Okay, so the first thing that we want to do is let's calculate the orientation of our line. And we're going to call that var theta. So let's say that's the orientation of our line. And again, so if we draw, this is our north axis, right? What I'm talking about is what is the orientation to get to that vector? That's var theta. Okay, so that's the orientation of our line. For the straight line case, or the case where we stay the same on, we have the same orientation of each circle, this is fairly easy. So we'll note that the line between the circles runs parallel to the line between the center points. So that I'm going to call this point right here, I'm going to call Z1, and this point right here I'm going to call Z2. So the line between the center start and the center end is parallel to the line that goes from Z1 to Z2. And the reason I'm using Z1 and Z2, you'll see soon that that'll match our notation for when we define the switching conditions. So this is really great because we already know what C1 and our starting and ending centers are. So because the line is following its parallel, then it's going to be the same, this is going to be the same angle, right? We have var theta. Okay, so we know that that's going to be the same, and so we can just calculate that var theta is just going to be equal to the a tan 2 of, oh yeah, so we have our east location for, our end east minus our start east, and then we have our C, our end north minus C start north. Okay. And I actually made a mistake here. I'm going to call this var theta is actually going to be defined by the line between the center points, because that's going to be the same for both of them. Okay, so but now we know that the orientation of our line is going to be var theta. So it's going to be the same for both of these. But I'm going to draw it along the center point because it's going to be different when we look at the other set of circles. Okay, now we want to know the length of the line. And the length of the line is just going to be the distance between, since these two lines are running parallel, the distance between, we'll call it L, the distance between Z1 and Z2 is actually just going to be equal to the distance between our center start and our center end. So now we know the length of that line, which is fantastic. Let's now look at the angle between our C start and the Z1. So now what we want to do, we'll call this guy var 2. And we call it var 2 because that's the angle that we have when we're going to be leaving the circle. Okay, so if we take a look at this, var 2 has a nice relationship with, or I keep calling it var. I have var theta 2. So var theta 2 has this nice relationship with our var theta, right? Because we know that these two lines are parallel, so there's a 90-degree angle between them. So if var theta points to that direction, now we want var theta 2 to be pointing towards that. And so we'll say that, or the angle to the line that points from the center to Z1, right? So var theta 2 is the angle from CR to Z1. Okay, so the angle between that, we're just going to take our var theta and we'll rotate it backwards by 90 degrees. So var 2 is equal to var theta minus pi halves. Which is so now we know the orientation of that one. And then we're going to call the orientation between our end circle and our point Z2 as var theta 1. Okay, so var theta 1, it's the angle from for the vector that points from ZR, our center end, to Z2. Our end center to Z2. So we'll call that var theta 1. Excellent. So var theta 1, now if we take a look at that, that's going to be equal, since the line between the centers and the line between Z's are parallel. So we know also that the line between C start to Z1 is going to be parallel to the line from Cn to Z2, right? So our var theta 1 is going to be equal to var theta 2. Okay, So that's really nice. So good, easy relationship there. And then the last thing that we're really going to need to know is the angle from what was it? Oh, of the line. Oh, I already calculated that. So we have the angle of the line Z1 to Z2. And this is just going to be equal to var theta, like we just mentioned, and a unit vector. We could write Q being the vector that points along that line. We're going to call that unit vector. We could write it in two different ways. We could say that that's the cosine of var theta, sine var theta, 0. Or we could also say that this is going to be equal to our C end minus our C start. Whoops, that was not a C. C start all over the magnitude. So we make it a unit vector. So we could express that in two different ways. Right? So now we've defined everything that is on that line, which is really great. And we could easily also define what our points Z1 and Z2 are just based on rotating a vector of radius r from CR all the way up to get it to Z1. So we have that negative pi half rotation. Okay, so let's go do all of this again for this slightly more complicated case. So now in this case, we're going to define our line between our center points, right? And I should have defined this as our center start and our center end. And the first thing to note is that the blue and the red lines are definitely not parallel, right? So this is our point Z1 and this is our point Z2. Okay, so those lines are not parallel. So what we're going to do is we're going to have to work on defining them. But we will note that since we have that CS, the line CS to Z1 is parallel to the line CE. Whoops, sorry. We'll just note that these two triangles are very similar. So what we're going to do is we're crossover. We're going to have this length M is going to be equal to that length M. And this length right here is the length of our line over 2, the line between the two center points. And this one's line over 2. Okay. So we have these two equivalent triangles. And we'll note that this guy right here, this angle we're going to write as gamma. And this angle right here we're going to write as alpha. Okay. So we have some notation. All we need to do now is solve for these variables. Okay. So let's go ahead and start doing that. So first we're going to solve for alpha. And we're going to use the law of sines. I didn't denote also that we have the radius there for both of them. Okay. So we use our law of sines. I'll do the sine of alpha over our radius is just equal to the sine. So now we'll use pi halves over L over 2. Sine pi halves over L over 2. And note that L is just defined as the distance between our start and our end points. So we already have that. Based on our start and end points, or start and end center points, then we can define what our L is. Okay. So sine of pi halves is equal to 1. So this is just equal to 2 over L. And so we have sine of alpha is equal to 2r over L, Or we could say that alpha is equal to the inverse sine of 2r over L. Okay, so this is where we have to have sufficient distance. So we have 2r over L. So this is something to note. 2r must be less than or equal to L. Otherwise, this is not well defined. So if we have sufficient distance, like we mentioned in the cases up above, right? We have two missing cases because we're assuming that we have sufficient distance. And that's where that distance comes in. Okay. So we have our alpha now well defined. Gamma we can get, oops, we'll go back to blue. Solve for gamma. We know that the angles inside of a circle are going to add up to pi. And so in this case, we can just say that gamma is equal to pi minus pi halves, because we have that right angle, minus alpha, which is equal to the inverse sine of 2 pi over L. So that's perfect. So, which is just equal to pi halves minus the inverse sine of 2 pi over L. Okay. So now, again, we define the angle from the north axis down to the line that points from CS to Z1. We're going to define that still as var2. And the angle that points from CE to Z2, right, from the north axis, we're going to define as var theta 1. Okay, so we have, let's look at var theta 2. So let's solve for var theta 2. So if we take a look at this, we have that var theta 2. We have this nice relationship where we could define the relationship between var theta 2 and we have gamma, and we still have the angle from the north to the line between our center points, that we define as, var theta. Excellent. So we're going to, var theta 2 is fairly simple to solve for now that we have a gamma. So we know that var theta 2 is just going to be equal to var theta, subtract off gamma. So we have var theta minus pi halves plus our inverse sine of 2, that was supposed to be 2r. 2r. Okay, 2r over L. Excellent. So now we have our var theta 2 well defined. So var theta 1, right? Note that these two, I started to write it up earlier. I wanted to, the line between our starting point and Z1 is parallel to the line between our ending point and Z2. So now this is where we need that. So we have line A and line B are going to be, well, I didn't write A and B. But we have the line between CS to Z1 is parallel to the ending point to Z2. And so we know what V theta 1 is in terms of V theta 2, because all we're going to do is, if we had V theta or var theta 2, and we're just going to add pi to it to get to var theta 1. Okay, so solving for var theta 1, this is just going to be equal to var theta 2 plus pi. Okay. Now, what is the angle now of our line? If we get this just a little bit bigger, right? So what we want to know is what is the angle of this guy. Okay, now we call that, well, we don't have a name for it. So we have the angle of our line. This guy would just be equal to, if we look at var theta 2, right? Var theta 2 points along this direction, right, from CE to Z1. Well, this angle that points along the line is just var theta 2, and we're going to add pi halves to it, right, for this circle. So we'll do var, so it's just going to be equal to var theta 2 plus pi halves. Okay, so we could then write a unit vector as q is equal to, and this unit vector q again is pointing in this direction. So q is a unit vector pointing from z1 to z2. z1 to z2. Okay, so our unit vector, again, we could write as cosine of var theta 2 plus pi halves, sine of var theta 2 plus pi halves, and 0, assuming planar. So we have that unit vector. Okay, the last thing we need to solve for is m, or the distance along our line. So the distance between Z1 and Z2. And we note that this distance, Z2 minus Z1, if we look at these triangles, it's just going to be equal to 2m. Okay. Now I'm going to write the rest of this. We want to have that notation up there so you can see. Well, we've solved for, we know what two of the sides are, right? Radius is given, and L over 2 we can calculate from where our center points are. So we can then come in here and we can say that our radius squared plus m squared, just using Pythagorean's theorem, is equal to the L over 2 squared. So let's now solve for I just keep wanting to write pi, m. There we go. So m is going to be equal to the square root of, we're going to L squared over 4, I just did the square of 2 on the bottom, minus r squared. And so then if we write that the length of Z1 minus Z2 is equal to 2m, oh, I almost wrote pi again, 2m, that equals to 2 square root of L squared over 4 minus r squared. Well, we can bring this 2 inside. We're going to square it, right? We'll bring that inside, and we'll write that this is going to be the square root of the 2 squared is going to be 4, so it cancels out with the 4 on the bottom, minus 4r squared. Okay, so now we have the distance that we travel along the line. Perfect. So in summary, we can come through, we can calculate the distance along each line. We can calculate the angles between them. From those angles on the previous slide, we could then, giving our starting orientation and then our ending orientation, we could then calculate arc lengths. And so we did this for both the right straight right and the right straight left. And you could take this and you could then apply it to the other cases of left straight left and left straight right. Okay, and so you could do similar calculations to get out these unit vectors, or these parameters. We're gonna end up using these unit vector quite a bit. For our switching conditions, we'll use the length. We'll also use our var thetas, our var theta 1 and var theta 2, as well as our var theta. And we'll also use that length. right? And var theta 1 and var theta 2. Okay, so we have all of these different parameters that now define the geometry of the Dubins path. And we'll utilize that to then describe the path length. And we'll do that in the following lecture.